not even my fault. Like, I wasn't recognizing, I wasn't doing what you did.
I couldn't believe it. Oh no, it wasn't wrong. Reading the song. I know.
Always drive though. I'm always driving. Yeah. I was and so like for all-wheel drive, you get through the tail with the understeer, but you can still control it with the understeer. It's like,
Yeah. I think really
I almost because I was driving on PCS when and there was this puddle, like a huge puddle with a lot of money. I drove through it like I was like not a big deal. I was in like 55. I go through it like some puddle for 40 feet belt, so I can't make it. And so like I go to whoever's there, I'm right away. It was okay. And I'm like curves. Like I had like
yeah, so I missed the actual testing, turn and review. My grade is good enough as it is, but if I can turn the reviewing now, would that help?
It can't hurt.
Yeah, right, well, I don't know. I'll turn it on.
All right, everyone, please take out your notes. If you recall the end of class last time, I went through the mathematical derivation of what is called the work energy theorem.
Hey, Nash.
Now, the work energy theorem is the following expression. Net work results in a change in kinetic energy. Now, what this equation says is that when net work is done on an object, that results in either A, a transfer of energy to the object, or B, a removal of energy from the object. The transferred energy, whether or not it be transferred to or removed from the object, results in a change in the energy associated with the object's motion, the object's kinetic energy. Remember that a moving object must contain energy because a moving object has the ability to do work on something else. So what we're going to see today with 4 examples is practice using this equation for simple dynamical situations. And when we look at these situations, they're all going to be familiar. We've seen them before. We're going to get a much deeper understanding as to exactly what is happening in these situations in terms of energy transfer. Let's start off today with the following. Now we've seen this situation before. We saw this situation before as a basic example in dynamics in chapter 5. When we saw the problem in chapter 5, we solved the problem by using F equals ma and then a little bit of kinematics. When you solve a problem in that method, you are using what is called Newtonian mechanics. You are using F equals ma as your starting point and then going from there. What I will do here is a brief repeat. First is I will solve the problem that old way as we saw it back at the beginning of chapter 5. But then what I'll do is solve the problem a second time. But when I solve the problem a second time, we'll use the work energy theorem as our starting point, and we'll get a much better understanding of the energy transfer that occurs in this situation. Okay, now the situation is nothing more than the following. The problem begins the instant that I let go of the eraser, in this case the hockey puck. It has a speed of 5 meters per second the instant I let go of it. It then slows down due to kinetic friction, comes to rest somewhere. We have to figure out where that is. So this is a familiar situation. We've seen it before. Now if we're going to set the problem as we saw it back in chapter 5, then we would have approached it in the following way. what you'll see here first is this version of the problem using Newtonian mechanics. That is, we used F equals ma as our starting point and then go from there. So very simply, we have the following. First of all, we have the hockey puck itself. It has an initial velocity v0 to the right-hand side, 5 meters per second. There's a little bit of kinetic friction here. Coefficient of kinetic friction is equal to 0.2, and the puck eventually comes to rest over here where the final velocity is 0. So the unknown that we're asked to calculate here in this problem is the displacement. Using here the notation now of chapters 7 and 8, the displacement here is the vector delta r. Okay, then as the eraser slides to the right-hand side here after I let go of it, there's only 3 forces acting on it, and they're as follows. We first of all have vertically the normal force of gravity, just canceling each other out. No acceleration, of course, in that direction. And then opposing the motion, which remember is described by the displacement vector, is the force of kinetic friction acting to the left-hand side. And because that's the only force here acting horizontally on the eraser as it slides across the desk, it is the force of kinetic friction, which then therefore gives us the acceleration. So when we add up the forces here horizontally, we just have one of them, and that's the force of kinetic friction. So the force of kinetic friction is then therefore equal to the net force mass times acceleration. Now recall, of course, from early on in chapter 5 that the force of kinetic friction is equal to the coefficient multiplied by the normal force, like so. And from above, the normal force is equal to the object's weight in this horizontal situation. So plugging that in appropriately like so, we would then just cancel out the mass, and we now have our expression for the acceleration. So the acceleration of the puck toward the eraser as it slides across the desk is the coefficient of kinetic friction multiplied by the normal force. So numerically here, that's just equal to the following, 0.2 times 9.8, and that comes out to be 1.96 meters per second squared. And then to find the displacement, like we would have done, say, in chapter 2, we're going to use here very simply the third kinematics equation to find the displacement delta r. I'm going to write the third kinematics equation, however, here with that slight change in notation that we saw at the end of class last time. Now, when we originally saw the expression back in chapter 2, the displacement was x minus x naught, final position minus initial position. That's the same thing as the displacement vector delta r. So to solve for delta r, first of all, plug in here the final velocity being equal to 0. Up comes to rest recall, like so. And then just running through the remainder of the algebra here, I have to solve for the displacement delta r. So move the v0 squared to the other side, like so. And then divide by 2 times a here on both sides of the expression to get the displacement by itself. That would then give us this. You know, we need to be a little bit careful when plugging in our negative signs here into this expression, because if I call to the right-hand side here the positive direction, remember the acceleration is to the left-hand side. When I plug this number in, I have to make it a negative number, because remember that all the quantities that are being described here are vectors, positive to the right, negative to the left. So the negative sign that I have to give the acceleration here will cancel out with this negative sign to give us a positive displacement to the right-hand side. The negative signs work themselves out as they should. So the numbers then very simply are as follows. 5 squared divided by 2 times 1.96. All the negative signs cancel out. So punching that in appropriately gives me a distance here of about 6.38 meters. Okay, easy enough to solve, a basic chapter 5 problem, but notice that the problem says nothing at all about the energy transfer that occurs. Now we start to take a look at that here using this new method of solving the problem. We now use the work energy theorem. When using the work energy theorem, your starting point is always the same thing. Net work equals change in kinetic energy. Now you approach the equation in the following way. You always deal with first the right-hand side of the equation. The right-hand side of the equation is always the same thing. It's the final value of kinetic energy minus the initial value of kinetic energy. Now remember what the basic form of kinetic energy is from at the end of class last time. Kinetic energy, capital K, is the following expression, 1/2 mv squared. So on the right-hand side of the equation, what I have to do here is take the final value of 1/2 mv squared, which in this case will be 0, minus the initial value of 1/2 mv squared, where the speed is the initial speed, v naught. So the right-hand side of the equation here is final minus initial kinetic energy as applied to this problem. It looks like this. And then the left-hand side of the equation is basically what we did last time in class with our practice problems when we calculated the work in simple situations. That is, you calculate the work done by the individual forces, you set up those dot products, and then you add it all together to get the net work done. That's then what gets plugged in here on the left-hand side of the expression. So now, like last time, we have to take a look at our force diagram here to show the relationship geometrically between the force vectors and the displacement. So the first thing to take a look at is the work done by the normal force. Okay, just go ahead and place it all here for me. Okay, now from last time in class, remember that you calculate the work done by a force by finding the dot product between the displacement vector and the normal force vector itself in this case. Now remember how this process is done from last time. We take first of all the magnitude of the first vector, multiplied by the magnitude of the second vector, multiplied by the cosine of the angle between the two vectors. If you take a look at the diagram above, note that the angle between the normal force here and the displacement delta r is 90 degrees. And then the cosine of 90 degrees is equal to 0. Now, in terms of energy transfer, we now know what this means. When no work is done by a force, that force does not transfer energy to the object, nor does it remove energy from the object. Hang on a second, Zach. Let me write that down. So this force does not transfer energy to or remove energy from the object. Remember that the role of work is to transfer energy. So then therefore, if no work is done by a force, no energy is transferred, either to the object or from the object in this case. So recall some of those practice problems that I did in calculating work last time in class. We posed these little questions associated with some of the calculations. Now we're beginning to answer those questions. Okay, Zach, you had a question a moment ago before we move on.
Yes, so why is the acceleration going left? if
Well,
the
the acceleration is caused by the force of kinetic friction. It's the force of kinetic friction that's slowing the eraser down after I let go of it, like so. Remember that the problem begins the instant that I let go of the eraser. In this case, the hockey puck itself has an initial speed of 5 meters per second to the right-hand side. Okay. Okay, next, continuing with these work calculations, we have two more forces here to worry about. The next one is the work done by gravity. Notice that the work done by gravity, which is once again this dot product here, is also going to be equal to 0 in this problem for the exact same reason as it was mathematically for the work being done by the normal force being equal to 0. Notice that between mg and delta r, there is a 90-degree angle. Cosine of 90 degrees is equal to 0 when calculating the dot product. So the work done by gravity is also equal to 0 for that reason. And then lastly, of course, is the work done by kinetic friction. So we have to set up that dot product. This is one of the things that we saw as practice last time in class. Now, with regards to a problem such as this, where the displacement is horizontal, the work done by friction is always going to be the same little expression. Here's how we find it. First of all, you have to set up the dot product between the frictional force vector and the displacement vector. Notice here from the top diagram, as is always the case with kinetic friction, there's a 180-degree angle between the force of kinetic friction and the displacement vector. Remember that the force of kinetic friction always opposes the motion, which is described by the displacement delta r. So when we calculate this quantity here, we'll have the force of kinetic friction, its magnitude, multiplied by the displacement, and then multiplied by the cosine of 180 degrees. The cosine of 180 degrees is equal to -1, so the work done by kinetic friction is always going to be a negative number. Now, in terms of energy transfer, we now know what this number means. If the work done by a force is a negative number, then what that force does is it removes energy from the object. In the case of friction, Where it transfers the energy to, we'll get to in just a few minutes. But for now, when the work done by a force is negative, that force removes energy from the object. Okay, now before I take the work done by friction and then stick it over here into the left-hand side of my work energy theorem, a couple of more steps we have to carry out. We have to write the force of kinetic friction here as the coefficient multiplied by the normal force. And then the normal force from our force diagram above, remember, is equal to the object's weight in this horizontal situation. So the work done by kinetic friction then along this horizontal surface gives you the following expression. It will always be that expression as long as the displacement is along a horizontal surface. So now that I have the work calculated by the individual forces, we then just add them all together, and that's then the net work here. That's what gets plugged in to the left-hand side of the work energy theorem. So I have 0, first of all, for gravity and for the normal force, and then add that to the work done by kinetic friction. That's then what goes here into the left-hand side of the equation. And now before I solve for whatever it is that we're looking for, what's most important about this example and the 3 others that I'm going to do today is understanding, at least qualitatively, how the energy transfer occurs. In order to see the energy transfer here in this problem, all that I'm going to do with my 2 expressions here is cancel out the negative sign from each side. Now when I cancel out the negative sign here from each side of the expression, I then arrive at the following equation. Think of this equation here as a description of what becomes what. What form of energy becomes another, what form of energy gets transformed or transferred in this situation. Now the right-hand side of the equation, we know what that is. The puck has an initial speed of v0, so this right here is the object's initial kinetic energy. And then, what the expression is saying is that the object's initial kinetic energy is becoming this due to kinetic friction. The question is, however, now, what is this? Well, this right here is another form of kinetic energy. It's the kinetic energy that makes up the molecules of a substance. In this case, it's the molecules of the desk, for example, as the eraser slides across to it. This other form of kinetic energy, the kinetic energy of the molecules of a substance, is referred to as heat. This number right here, whatever it happens to be, is literally the amount of heat that is transferred to the surface below. Now you already have some familiarity with the concept of heat from chemistry class. For example, it's one of the standards that is covered when talking about chemical reactions, at least in theory. Heat is the kinetic energy of the molecules of a substance, in this case the ice or the surface of the desk. So you studied heat, at least I hope you did, in the context of chemical reactions, regardless of whether or not they were exothermic reactions or endothermic reactions. That just then told you whether or not the heat was dumped into the reaction or came out of the reaction. But heat is just another form of energy. It's the kinetic energy of the molecules of a substance. Does anybody recall the basic metric SI unit of heat? It's a calorie with a lowercase c, not a capital C. Calorie. Uppercase C, by the way, a food calorie is actually a kilocalorie. It's 1,000 of these guys here. Does anybody remember what the definition of 1 calorie is, the lowercase c? Does anybody remember? Nash?
Is it like the amount of energy required to heat 1 gram of water 1 degree Celsius?
Yeah. Take 1 gram of water, very small amount, heat it up 1 degree Celsius. The amount of energy necessary to do that by definition is called 1 calorie. Now, if this number here, a mechanical form of energy, was equal to 4.2 joules, that would be the energy necessary to take 1 gram of water and raise its temperature 1 degree Celsius. That is, it's equal to 1 calorie. 1 calorie is the equivalent of 4.2 joules of mechanical energy. So this literally right here is the amount of heat that is transferred from the object to the surface below. So just qualitatively, it's very easy to understand. As the eraser is sliding across the desk, the eraser itself is doing work on some of the molecules that make up the desk, thereby transferring energy to those molecules. If I had a sensitive enough thermometer and I measured the temperature of the desk before the eraser slides across it, and then the temperature of the desk after the eraser slides across it, I would find that the temperature afterwards is a little bit more than it was previously because energy was being transferred from the eraser to the desk by kinetic friction. That's exactly what this number here means. Notice that the top board, Newtonian mechanics, says nothing at all about this. So qualitatively, this red step right here showing the energy transfer, that's the most important part of the problem. Okay, now we're just going to algebraically finish the problem. I'll do that over here on the right-hand board. Let me just recopy the expression briefly. And then recall what I'm supposed to solve for here in this expression. I'm supposed to solve for the displacement here, delta R. So the next step is to just cancel out the mass from each side of the expression like so, and then divide by the coefficient times g to get the displacement by itself. And when you do, you arrive at the following equation. So, now compare that expression that I just wrote down to this expression from the displacement earlier when I solved the problem by using F equals ma. Is that equation there the same thing as this? Yes, it is. Because here in the denominator of this expression is the acceleration, which remember was the coefficient multiplied by g. That's the same thing here. So because the equation is the same, of course the number is the same thing. It's 6.38 meters. Now there is a slight difference between the two equations. This one here has a negative sign, for example, whereas that does not. The reason for that is as follows. Remember that everything up here on the top board, F equals ma and kinematics, blah, 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 all of this is vectors. Positive to the right-hand side, negative to the left. So this right here is a vector equation. All the stuff that we've done right here, however, with the work energy theorem, all of that is basically dot products. And dot products always give you the magnitudes of the vectors. So this expression right here is a scalar. This is a scalar equation. But other than that, numerically, of course, it's the same value, 6.38 meters. What this means is that in theory, you could actually set up any problem in dynamics with either method, F equals ma, and then solve for whatever it is that you're looking for, or the work energy theorem, and then solve for whatever it is that you're looking for. In theory, you could use either method to set up and solve the problem. Sometimes one method may be a little bit easier than the other, but in this case, both of the methods are pretty straightforward. But the one advantage in terms of just deeper insight into what's actually happening that the work energy theorem has over F equals ma, that we have an understanding of the energy transfer. So with my remaining 3 examples today, we'll also see the energy transfer that occurs in those examples as well. Okay, as a nice little sequel or a part 2 to this problem, let's take a look at the following example. Okay, this is once again just going to be a horizontal displacement problem. In this case, an object will start at rest, and then it's just pulled horizontally by some constant force. So I'm just going to pull the eraser across the desk. I'll do so over a displacement, given that this problem is 3 meters, and then we'll calculate the final speed of the object as the problem ends. Now with this example and the 2 more that I have for today that will follow, I'm just going to solve the problems entirely now by using the work energy theorem. I'm no longer going to use F equals ma. right, now in this particular example, all that's occurring here is that the eraser is starting at rest, and I come along and I just do this. Like so. The problem ends the instant that I let go of the eraser. It has some final speed after it's been pulled over a displacement in this problem of 3 meters. As we do this, I apply a constant horizontal force of 20 newtons, and there's a little bit of kinetic friction. So as I start to draw out the example, I then start to see the following. So here's my surface. As I said, a little bit of kinetic friction like so. Here's our object, my eraser, or this box as it's called, of 1 kilogram. And then we'll start with the object initially at rest. And then I come along, and I exert a force here, constant force horizontally, F pole we'll call it, equal to 20 newtons like so. We'll do so over a displacement here, delta R of 3 meters. And then the problem ends the instant that I let go of the eraser or the box, and it has a final speed V that we're asked to find. Now, even though I'm not going to use F equals ma to solve the problem here, you still draw out a force diagram because you need to show the relationship geometrically between the force vectors and the displacement vector in order to calculate the work done by those forces. So as I pull the eraser to the right-hand side, I would have the following forces acting upon it. First of all, once again, vertically, have the normal force and gravity cancel each other out. I would have my F pull here to the right-hand side. That's the force that I exert. Keep in mind that the displacement vector here, delta R, is to the right-hand side. That then means that the force of kinetic friction opposes the motion, thereby pointing to the left-hand side, like so. And then we start to set up our equation in the following way. We have net work is equal to change in kinetic energy. This is always the opening step. And then the next thing that you do is you always look at the right-hand side of the equation first. The right-hand side of the equation, as I said earlier, is always the same thing. It's the final value of 1/2 mv squared minus the initial value of 1/2 mv squared. So final kinetic energy, 1/2 mv squared, minus initial kinetic energy, which is equal to 0, because the object begins at rest. Incidentally, with all the problems that you'll see me do today, the 2 thus far and then 2 more to follow, I'll either start with the object at rest or end up with it at rest, just because it's easy to describe here for lecture purposes. That doesn't necessarily, however, always have to be the case. Okay, now we get to the left-hand side of the equation. The left-hand side of the equation is always the same thing. Calculate the work done by the forces, add it all together to get the net work done. So let's immediately take a look at the normal force once again. Okay, tell me, what is the work done by the normal force here in this problem and why?
0.
Okay, it's 0 once again.
It's 96.
Yeah, the normal force is perpendicular to the displacement vector. The work done by the normal force is equal to 0. Once you become proficient in doing these calculations, you can actually begin to shortcut some of this. You can immediately write down that the work done by the normal force is equal to 0, or quite frankly, as long as you understand that, you don't even have to bother writing it down. Now, in the 2 examples that we've seen here, the work done by the normal force has been equal to 0, which means that no energy is transferred to the object by the normal force, nor does the normal force remove energy from the object. But remember that the normal force can do work. But something else has to be present in order for that to occur. Recall the following from last time. So right now there is a normal force acting upwards on the calculator. And I do something like this, meaning that yes, in this case, work is being done by the normal force. But I'm necessary for the normal force to do work. The reason why is you have to have an energy source present in order for the normal force to do work. What I mean by that is the following. If I just place the calculator here on top of the book on the desk, is the book ever going to do work on the calculator? No, you're never going to see the book do all of a sudden this to the calculator. The reason for that is because the energy necessary to do that would have come out of nowhere. It would have been created. So then therefore the normal force can't do any work for this reason. The only way that the normal force can do work is if there is an external energy source present. That would be me, for example, lifting the book like so. So I hate to tell you this, guys. It turns out that all superhero movies are incorrect because they all violate a very simple principle in nature, and that's conservation of energy. You guys remember in X-Men 3 when Magneto picks up the Golden Gate Bridge and then sets it out over San Francisco Bay? not gonna happen. The reason why is because the energy necessary to do that came out of nowhere. So the basic law of physics that all superhero movies violate immediately is conservation of energy. That means that it's just pure fantasy. Jenna?
Does that mean you never actually lift anything? The normal force does it?
I'm sorry?
Do you never lift anything? Does the normal force like?
No, I mean now I'm lifting the calculator directly.
uh,
But right now, technically speaking, it's the normal force acting on the
Oh, 'cause
calculator
you're
that's
holding
lifting
the
the
book.
calculator. But I'm lifting the book, of course, that's causing all of this. So I'm supplying the energy necessary for that to occur. If I'm not there, then it's
it
never
will
going to
never
move
happen in
upwards.
nature.
Never.
Okay.
Okay, yes.
So as you lift the book upwards, there's normal force being applied to the calculator. Is there a negative normal force going downwards?
Well, I mean, there's a force acting downwards on the book from the calculator pressing it. Okay, we could deal with that mathematically if we wanted to, but it's not important for our purposes here to understand.
If you were to drop the book, like say you drop the book and the book falls faster than the calculator?
No, they will follow the same acceleration downwards of 9.8 meters per second squared as we studied back in chapter 2.
I gotcha.
That
always
always
Right.
weird thing.
That last question.
Did you see that article that of the physicist who described the physics of Thor's hammer? It was really
Yeah, right.
fun. I don't know, it was actually very interesting.
It was just a comic. Don't worry, I liked comic books too when I was a kid. I actually had a huge collection of comic books. I eventually sold the whole thing about 15 years ago for about $15,000 on eBay.
Awesome.
Wow.
I must still regret it to this day.
Comic book.
Really?
Yeah, I had a huge collection of Marvel comics when I was a kid. Okay, just continuing with our calculation. Okay, like in the last example, because this problem is also horizontal, the work done by gravity is equal to 0. Mathematically, for the exact same reason as it was in the previous problem, force of gravity here, mg, is perpendicular to the displacement. Cosine of 90 degrees is equal to 0. Okay, and then we get to F pole, which wasn't present in the first problem, but is present here. Now, when I say the work done by F pole and set up that dot product, remember that I'm the one who's supplying that force. So technically speaking, this is the work done by me. So the work done by me is equal to the dot product between the force that I exert and the displacement over which that force acts. Notice that in this simple case, the F pole and delta R are in the same direction. There's a 0-degree angle between them. So when I calculate this dot product, I'm going to have the cosine of 0 degrees, cosine of 0 is positive 1, and I end up with just force times distance. So, notice that this will be a positive number. In terms of energy transfer, that now means that this force transfers energy to the object. So by me pulling on the eraser, for example, I transfer energy to it. So this force transfers energy to the object. So this then answers all of those little questions that I posed here when we did these work calculations last time in class. Basically, when the work done by a force is 0, no energy is transferred. When the work done is positive, as it is in this case, energy is transferred to the object. If the work is negative, energy is removed from the object. Easy enough. And then lastly here, we get to kinetic friction. The work done by kinetic friction here in this problem will be exactly the same formula as it was in the previous example with the hockey puck. Once again, here's how that goes. So initially, here's our dot product. We also note immediately here that there's a 180-degree angle, as is always the case, between f sub k and delta r. Cosine of 180 is equal to -1. We always pick up our negative sign for that reason. Guys in the back, you have to stop talking, please. Okay, now the force of kinetic friction is the coefficient times the normal force, and yes, the normal force is once again equal to the object's weight. So then therefore, you end up with this same little expression here for the work done by friction on a horizontal surface, as we saw in the previous example. It always is this little expression. Now that I have the work done by calculated, that is, by all the individual forces, now we just add it all up. That's then what goes here on the left-hand side of my work energy theorem expression. So I have over there first the work done by F pole, plus right here the work done by friction, and then remember that the other two forces do no work, and then therefore I end up with this expression here. Now before we just do the remainder of the algebra here to solve for the speed v, what I'm going to do instead is one more step to show the energy transfer. And once again, it's specifically from a qualitative standpoint, the energy transfer itself that's most important to understand. So to show the energy transfer here in this problem, what I'm going to do is the following. I'm going to take the work done by friction there and move it to the other side of the equation. That will then give me this. Like so. So take a look at that carefully. All that I did was I moved the friction term here to the other side of the expression. Always think of this energy transfer equation where it's what becomes what form of energy becomes another. So here on the left-hand side, remember that this right here is the work that I did in pulling the eraser across the desk. In other words, this is the energy that is used by me, the energy used by the external agent in this problem. This is the energy used by the person. And so then therefore, what's happening to the energy that I use? Well, it's turning into two things. It's turning into, first of all, a little bit of heat due to kinetic friction, and it's also turning into the kinetic energy of the object itself as I pull it across the desk. This is intuitively obvious if you just watch it happen. As I take the eraser and pull it across the desk like so, the energy that I'm using to do the work here is turning into two things. The energy associated with the motion of the eraser itself, and also a little bit of kinetic friction, causing some of the energy to be transformed. Easy enough. Okay, then just to solve for the remainder of the problem, however, mathematically, I'm just going to jump back to this step right here, and what I'll do now is multiply by 2 on both sides, divide by the mass, and then take the square root. When I do this, I'm calculating a speed. I'm not calculating a velocity, I'm calculating a speed, because remember that ultimately everything in this expression came from dot products, which only give you scalar quantities. So this is not a velocity vector, it's just the magnitude of it, it's just the speed. So let me see, doing the math here, cross multiply by the 2 and the m, take the square root appropriately, and that will then give you the following expression here. Go ahead and just place it on your desk, please. Thank you. Yeah, right there's fine. Like so. And now I just plug in my numbers to get my answer in terms of meters per second. So numerically, I'll do the parentheses here first. I have, first of all, 20 times 3, that's 60 joules. This right here is the amount of energy that I use in this problem. So 60 joules, well, let's see, it's minus 0.3 times 1 times 9.8 times 3. So minus 0.3 times 1 times 9.8 times 3, all times 2 over 1, and then square root the whole thing. And after all of that, the final speed turns out to be this number here. Once again, this is a speed, not a velocity. Okay, any questions on this example or the one previous to it? Yes?
That formula for heat, is that always going to be the same?
Yes, as long as it's a horizontal displacement, it'll always be the same. Okay? Okay, very good. Let's take a short break before we get to the last two examples.
Why is the speed not velocity?
The reason why is because, remember, everything here mathematically came from dot products. Dot products always give you scalars, they don't give you other vectors. So everything here is a scalar.
Oh, okay.
I'll do that.
It is my mom's car too.
Oh, which one? You wagon?
I don't know, I like asking if even is looking at what he showed us how goes are equal.
You should convince your mom to get a,
Oh, yeah.
the 63 wagon.
hinting something?
But it's a super bucket.
I'm feeling it.
It's a super bucket.
But still. If I were to add that,
Okay, you're not going to the basic bucket. How do you get it to the six?
right before I go.
rolling in it, but
And write it back.
With all the drives, you
The way my
can put in words.
like, I was like, so you guys just like,
Do you make that?
No. Okay, would you rather have an E6 wagon or a CSP wagon?
yeah, what did you say?
Okay, you take the E6, I'll take the CATSP. And I'll switch.
So did you measure how much did we get?
The ATSP is nice.
Okay, so Culver City, it was.
So the 16 like.
I was really
CTSP.
Yeah.
I don't know, the CTSP.
I live in Hermosa Beach, so I probably got about
The
six.
ATSP is all. I'm like,
That's what they were predicting, somewhere around 2. Yeah, I mean, it looks like it's tapering off now. Look, it's still
Oh, I was
decent.
saying Friday.
Yeah.
She's like, hopefully we'll get a lot more like this.
Alright, well, bye, Sean. Okay,
It's being used.
and that's, you say you're going.
Take that fast. I'm ambivalent about it. I like it, but I don't like it. I don't really like it. It looks too sharp.
What those books try and do is they try to take a popular character and then try to use that character to teach basic physics.
I know it's already thinking, I mean, it was.
Well, it's not fake. I mean, it's fake in the sense that, of course, assume it's fantasy. But he's saying, okay, this could happen this way, here's how it would work. That's basically what
And he's basically saying like, from a different planet, highly advanced, this could happen.
Some of those books are okay.
I know,
What we've actually discovered is that the drought is so severe that the entire western portion of the continent is actually floating higher on the mantle than it normally would.
What?
There's that much less water in the western portion of North America. So North America is actually floating a little bit higher on the mantle than it normally does because of the weight of the water weighing it down.
Oh, wow.
it's not bad.
That's how bad it is.
That's ridiculous.
I mean, when you put it in those terms,
Are you serious?
I wasn't paying attention.
because it's like, think of the continent as like, you know, like a boat, okay? And you put it on water, you put a bunch of stuff in the boat, okay? It's gonna get lower in the water. So if you take the stuff out of the boat, then it gets higher. Same idea. So if you take the water off the continent, it literally floats.
I don't know.
It's not that much, but it's minimal, which is kind of
Yes.
scary.
Nice. What?
Where's the cut?
Really?
Shoulders?
Oh.
Yeah, definitely can't see you, John.
She's like, wait on your gas.
No, can't see Jenna.
What about now, Henry?
I think it normally sees me worse than
Yeah, you too. Can't see Nash though. Now Jenna, you're out of the picture.
Damn it.
You want to be in the picture?
I used to am, but I think I'm right there.
Yeah.
Does anyone watch me?
I actually like went on one just to see.
But this is a good sign. Because this is, you know, we've had a couple of minor rainfalls already. We had one a few days ago.
I mean, 8
Yeah,
views,
the
that's
first
like
system.
8 apps.
That was, you know, weak, but it gave us a little.
People.
One person that has to reload it.
There was another sprinkle, I think, in somewhere in between as well.
I don't sleep that.
So, we've already gotten that thing. The last time that we really got a lot of them, like,
So many.
was the winter
I
of
always like
2009,
cars,
2010.
crash cars, I feel like
That was
back
like
because
the
I read
last
something and I was like, I
one.
keep feeling it never comes.
It's a while.
Well, if I did feel like it.
No, I don't know about history. I don't like biology. Biology?
There was actually a water spout spotted on
Oh, with bio stuff.
It happens once in a blue moon.
John
It's rare, but it happens once in a blue moon. Yeah, it's probably high enough. Yeah, the last time it actually snowed in the LA basin, like where it was actually on the ground sticking in the city, was 1972. That was the last time it actually snowed. But if you get a really cold winter storm, the snow level will drop to maybe 1,200 feet or so. That's about like the top of it. Top of it.
They just absorb it in their.
Get banged up. They'll get it dusted. Once in a while. Get it dusted.
What do I do?
You two don't even take notes.
I'm looking at you.
Last time it snowed in the LA basin, it actually stuck on the ground was 1972.
So wait, physics? I have a night before this class. Pencil back.
75.
I use
Or I have like an 83 in the test.
All right, let me go ahead and move on, please. So in my last two examples today here regarding the work energy theorem, they're just going to be backwards of each other. We're going to see a new form of energy that is present. Now in the first two examples that I did, no work was done by gravity because the displacement was horizontal. In these last two examples, first of all, see what happens. The eraser slides down the slope like so. And then secondly, if I release the eraser with some speed up the slope and it slides up the slope, in these two examples we will see that there is a new form of energy present that we haven't seen previously. Yes?
Does the angle of inclination change the coefficient of kinetic friction?
Usually, probably, I would say off the top of my head, probably not. The reason for this is because the coefficient of kinetic friction is basically a function of how these atoms here are interacting electromagnetically with these atoms here. Okay, so we're familiar with this situation. It's just an object starting at rest and sliding down an incline. We're going to calculate the final speed when it reaches the bottom of the incline. We'll do so by using the work energy theorem. Give me a moment to copy it down. All right, so our situation is as follows. Okay, easy numbers to work with here, once again in the example, a 30-degree angle. Coefficient of kinetic friction, that's equal to 0.1. And then we're starting here with the object at rest, v naught is equal to 0. Slides down the incline and reaches the bottom of the incline here with speed v that we're asked to calculate. As it slides down the incline, it undergoes a displacement. That's basically the hypotenuse of this triangle. That's the displacement delta r of 2 meters. Then as we saw last time in class, the height change here is going to become important when dealing with the work done by gravity. The height change here, h, remember, is equal to this hypotenuse multiplied by the sine of the angle. I'm actually going to go ahead and directly calculate this number because we'll need it in a few minutes in the equation itself. So this is 2 meters multiplied by the sine of 30 degrees, which is a half, so therefore the height change is 1 meter. Okay, now we still take a look at the force vectors as the eraser slides down the slope. We're going to have the following. First of all, the normal force, perpendicular to the incline. Force of gravity straight downwards, and then opposing the motion like so is the force of kinetic friction. Here's a right angle. Now the displacement is down the incline like so, delta r. And yes, even though we're not using F equals ma to solve the problem here, you still take mg and break it up into its normal components. So here's the perpendicular component like so, parallel component here, right here is our angle theta as always. And now we set up the work energy theorem. Once again, here's our opening step, the equation itself, net work equals change in kinetic energy. Now that you've seen me do this in a couple of examples, who can give me the right-hand side of the equation here? What's it going to look like? Brian?
1/2 mv squared minus 0.
He's exactly right. It's always equal to the final value of 1/2 mv squared minus the initial value of 1/2 mv squared. So the final value of the kinetic energy has to do with our unknown speed v. The initial value of the kinetic
Please
energy
excuse
is
this
0.
interruption. All soccer players, all of varsity JV need to be released today at 1:20. The games are being played at Pally. Teachers, sorry about this interruption. We just had a last-minute change. All soccer players are to be released at 1:20, by 1:20 today. Thank you.
Pick the ball and chase it. Okay, so the right-hand side of the expression is always the same thing. The final value of 1/2 mv squared minus the initial value. In this case, it starts at rest, ends up down at the bottom with the slope or the speed v. Then we have the left-hand side, which is once again always the same thing. The work done by the individual forces all added together. Immediately note the following. The normal force is perpendicular to the displacement. No work is done by the normal force. So in terms of energy conservation, what that then means is the following. If the incline is just sitting here, the incline does not have the ability itself to transfer energy to the eraser or remove energy from the eraser. In order for the normal force to do work in a situation such as this, an energy source, me, would have to be present. I would have to do something like this, like you've seen me do before here in this rather silly demonstration. Okay, then next we get to kinetic friction. When I calculate the work done by kinetic friction here, it doesn't matter whether or not the eraser is sliding down the slope, or as we'll see in the follow-up problem, up the slope. You're always going to get the same little expression. Here's how it's calculated. So we set up the dot product between kinetic friction and the displacement vector. Note once again, as is always the case, there's a 180-degree angle here between f sub k and delta r. Cosine of 180 is equal to -1. Okay, and then the force of kinetic friction itself is equal to the coefficient multiplied by the normal force. Remember that the normal force here is canceling out with the mg cosine theta here, the red side of the triangle, because there's no acceleration in that perpendicular direction. So this guy right here, the f sub k, is always the same thing, thereby giving you the following expression. And as we'll see in the later follow-up problem, it doesn't matter if the eraser is sliding down the slope as it is here, or later on if it's sliding up the slope, the work done by kinetic friction is always going to be the same thing. And then lastly, we have gravity. We saw this last time in class, but as a refresher, here's how that calculation goes. So we set up our dot product between the gravitational force vector and the displacement vector. So magnitude of the first vector times magnitude of the second, multiplied by the cosine of the angle between the two vectors. Now the angle between mg and delta r is this unlabeled angle right here between the two vectors themselves. Yes, in terms of the angle theta, this guy right here is its complement. Yes, she's correct, it's 90 minus theta. Smart code. Okay, so we saw this last time in class, remember. This is just a basic repeat of it for practice. What I'm going to use here is, once again, a trig identity. I'm going to use the trig identity to show that it's only the height change that is important. Here's how the trig identity works, if you recall from last time. So first of all, we have this stuff here on the front. And I'll put it here in brackets. What we now have is the following. Cosine of the first angle times cosine of the second angle, and then with the subtraction identity here, there's a sign switch, so it becomes plus sine of the first angle times the sine of the second on the side. Now the brackets, they're simplifying. Cosine of 90 in the first term is 0. Sine of 90 in the second term is 1. And then if you just clean up what is left over here, you then end up with the following. And there it is, hypotenuse multiplied by the sine of the angle, which, remember from the basic geometry of the triangle itself, is just the opposite side of the triangle, which is equal to the height change. So there's the MGH calculation once again. Okay, now that I have the work done by the individual forces all calculated out, we just add them together, and that then goes here into the left-hand side of the equation. So first of all, the work done by gravity, MGH, plus the work done by friction from a few moments ago. The normal force, remember, does no work, and that then equals a change in the kinetic energy on the right-hand side of the equation. And then in just a few moments, what we'll do here is the necessary algebra to solve for the speed v. But once again, what's most important about these basic examples is understanding the energy transfer that occurs. So to see the energy transfer, I'm just going to do one extra step. I'm going to take the friction term here and move to the other side of the equation. And when I do, we're now going to see a new form of energy that is present. So if I move the friction term to the other side of the expression, I then arrive at this. Like so. And always think of this expression as what becomes what. What form of energy turns into another. Now we're familiar with the two terms on the right-hand side of the expression. We have, for example, right here, the amount of energy that's transferred as heat from the object to the surface itself due to kinetic friction. And then, of course, we have right here the kinetic energy of the eraser, for example, when it reaches the bottom of the slope. The question is, however, what is this? Because this thing here, something that has to do with gravity and height, that's what's being transformed into heat and kinetic energy. So we're now beginning to see a new form of energy that is present. So, watching the demonstration very simply like so, something that has to do with gravity and height is being transformed into kinetic energy and heat as the eraser slides down the slope. What do you suppose this just might be? Maybe it's potential energy? Now, yes, it is, and I know that everybody here has probably at least a basic familiarity about what is meant by potential energy, but as you'll discover a little bit later on, exactly wrapping your head around exactly what is meant by potential energy and mathematically describing it is actually really tricky to do. So what I'm doing here is I'm using this example and the one that follows up to introduce the idea to you. A little bit later on, we'll actually define it and describe it a little bit more rigorously. For now, you're seeing it here for the first time. But basically, potential energy is turning into heat and kinetic energy as the object slides down the slope. Okay, and lastly, we just finished the math here algebraically. The way that I'll finish the math algebraically is just to jump back to this step here and solve for the speed v. So to solve for the speed v, just cancel out the mass m first of all from each term like so, cross multiply by the 2, and then take the square root. So after you do those minor mathematical steps, you end up with this rather ugly looking mess. So, and then we just go ahead and plug in our numbers. Now remember, we know what the h is from the top board. I calculated that earlier. That was 1 meter, so I'm going to plug that in. So doing the parentheses first, I'm going to have 9.8 times 1. And then we'll see if the coefficient is 0.1. So minus 0.1 times 9.8 times cosine of 30 times 2. So minus 0.1 times 9.8 times cosine of 30 times 2. Multiply all of that by 2. And then take the square root of the whole thing. And after all of that, it comes out to be 4.03 meters per second. But once again, qualitatively at least, is the energy transfer that's most important. And then lastly, as a follow-up, we basically just do the problem backwards. As I set this up backwards, hopefully immediately everybody here is going to be able to tell me what the energy transfer is that occurs in this situation. So you guys tell me, if I take the eraser and let go of it like so, so I give it some kinetic energy, what is that kinetic energy going to be turning into as it moves up the slope? Heat, number one, and what else? And potential energy. So I should see the equivalent statement of that red statement there, for example, where I should see it as kinetic energy becoming then equal to heat and potential energy as the object moves up the slope. So qualitatively, this is pretty simple and straightforward. Here's then how we begin to calculate it out. Jenna?
Is that v speed?
Yeah, it's a speed. The reason why it's speed and not velocity is because all of this stuff comes from dot products, so it's all scalars. That's right. Okay? Okay, so just setting up this last problem from scratch, it's different numbers. Yeah.
Are we gonna need some kinematics?
I'll just work energy theorem once again. So we've gone past Isaac Newton here. We're past Isaac Newton by about 100 years. So this is essentially early 19th century physics.
But I mean, you can figure out how far up it moves.
Oh yeah, we could do F equals ma and then kinematics and blah, 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 and get an answer. But now we've moved past that, we want to understand the energy transfer that occurs via the work energy theorem. Okay, so now setting this situation up from scratch, we didn't see this situation in our practice problems from last time, so there will be some differences. Okay, right here is our angle of inclination. Once again, 30 degrees to make the numbers easy. Okay, coefficient of kinetic friction, a little bit different in this case, is 0.2. Okay, now our object will start here at the bottom of the slope of the eraser, initially moving up the slope like so, with an initial speed of 5 meters per second. And then it ends up at rest somewhere up here. I'll just draw it at the top of this incline. Okay, now two things are unknown. We don't know what the displacement is. That's basically the hypotenuse here of this triangle. We don't know the delta R, nor do we know the height change for the exact same reason. Now the height change itself is still equal to the hypotenuse multiplied by the sine of the angle, but because we don't know what the delta R is, that's what we're trying to find in the problem, we don't know the height change either. When it comes to answering the question as it's posed, how far up the incline does the mass move, we could either calculate delta R or H, either one is perfectly fine, that answers the question. Okay, now as I said, this is not quite a situation we've seen here yet thus far with our practice problems from last time, so there are some minor differences. As the eraser slides up the slope, we have the following forces. Normal force perpendicular to the slope, force of gravity straight downwards, and then opposing the motion would be the force of kinetic friction, like so, pointing down the slope. Right here is a right angle. Remember that the displacement vector, delta R, is up the slope, so then therefore the force of kinetic friction opposes that. Okay, still take mg, break it up into its usual components like so, thereby showing the angle theta. Okay, now we set up our work energy theory expression. So net work equals change in kinetic energy. Somebody other than Ryan, who can give me the right-hand side of the equation?
The difference between the.
What's 0 minus?
It's 0 minus 1/2 m v naught squared. And the reason for that is as follows. Okay, yeah, final kinetic energy is 0, then minus the initial with the speed of v naught. So final minus initial kinetic energy will then therefore look like this. Okay. Okay, next we take a look at the left-hand side, the work done by the forces. Two of the forces immediately are going to be easy to deal with because we've already seen how they're calculated. For example, again, work done by the normal force is equal to 0. Notice that the normal force is still perpendicular to the displacement. Cosine of 90 is equal to 0, therefore the normal force does no work. Remember that I would have to be present in order for the normal force to do work. I would have to push the incline in some manner. Okay, then next we get to kinetic friction. Even though kinetic friction here is backwards in the previous example, when I calculate the work done by kinetic friction here, it's going to give me the exact same expression. Here's how it works. So first of all, here's the opening step. Dot product itself. As is always the case, note that we still have a 180-degree angle between f sub k and the displacement. So cosine of 180 is -1. We still pick up our negative sign for that reason. And then the force of kinetic friction itself is the coefficient times the normal force. The normal force here is still being canceled out, remember, by the mg cosine theta here, perpendicular to the incline, because there's no acceleration perpendicular to the incline. So the n here is still the same thing as mg cosine theta. So this guy right here then, therefore, is the following. Same expression going up the slope as opposed to what it was earlier going down the slope. Doesn't matter. Work done by kinetic friction on a slope problem such as this always gives you the same expression. Okay, then we get to gravity. When it comes to gravity here in this case, once again the work done by it is only going to depend upon the height change. And in this case it's going upwards as opposed to downwards. That will give us a slight difference. Here's what I mean. So now I set up this dot product. So this is once again the work done by gravity. So I have to take the dot product between gravity and the displacement vector. So we have magnitude of the first vector times magnitude of the second vector, and then multiplied by the cosine of the angle between the two vectors. Okay, let's see if Jenna can get this one too. What is the angle between mg and delta r in terms of theta up on the top below?
Plus 90.
It's 90 plus theta, that's right. So right here is the angle that we need, like so, between mg and delta r. So we need this big angle like so. Notice that that big angle is going to be 90 degrees plus the angle theta. So it's, I'm sorry?
Is that a new trig identity?
Yes, it is. It's just the addition identity, however, which is virtually the same thing as the subtraction identity, but it will give us a slightly different result. So yeah, there's the angle, and now we have a slightly different trig identity, as Jack correctly pointed out. And then here's how this works. Okay, first of all, we've got this stuff still here out in front like so. And now putting it in brackets, cosine of the first term, cosine of the second term, and then it's a sign switch. So we go from plus to minus. Sine of the first angle, sine of the second, like so. Don't worry, I'm not going to ask you to prove any of these trig identities. In theory, you've already done that. There's no need for us to do that here. Okay, now the result that we'll get here when I simplify the brackets is a little bit different than it was in the previous example. Okay, first off, right here in the first term, cosine of 90 degrees is still 0. Second term, sine of 90 degrees is still 1. And now we've got this negative sign here. So when I clean up this expression a little bit, you then end up with the following. So, the work done by gravity in this case, when the object moves up the slope, ends up being a negative number. It's still dependent upon the height change, but the difference here between this problem and the last one is that in the last problem, when the object was going down, the work done by gravity was a positive MGH. In this case, when it moves upwards, it's a negative MGH. But I'm still always kind of getting the same thing in the sense that the work done by gravity only depends upon the height change. Eventually, a little bit later on, we'll actually be able to shortcut our way past all of this rather horrible brute force calculation. It's necessary to do the brute force calculation a couple of times to see the result of it, which is this expression right here, this MGH term that we're now starting to see associated with gravity over and over. But eventually, once you understand that, and you eventually understand what is meant by potential energy, then we can shortcut our way past this horrible calculation. But for now, you have to see it done a couple of times. Okay, now that I have it all calculated out, now we just add the work done by the individual forces together to get the net work, place that into the left-hand side of our work energy theorem expression. So first of all, from the right-hand board, we have the work done by gravity, plus then from right here, the work done by friction. That then gives us our change in kinetic energy here on the right-hand side of the expression. Okay, now the energy transfer that occurs here in this problem can be seen from this equation right here if I only just cancel out the negative signs. If I cancel out a negative sign from each term, I then end up with the following. You get this expression here. And this expression here is exactly what we described at the beginning of this process, what you qualitatively told me was happening as the energy transfer occurs. So what we start with here on the right-hand side of the expression with the speed v naught, this right here is the eraser's initial kinetic energy at the bottom of the slope. And then, that initial kinetic energy is turning into these two things, like so. It's turning into heat, and then once again this term right here, which we're seeing again, this new form of energy, we're starting to think of this as potential energy, and that's what's occurring in the example. So once you get the hang of it, and yes, it takes some practice, qualitatively understanding the energy transfers that occur in these simple dynamical situations is actually pretty easy. Kinetic energy at the bottom of the slope turns into heat and potential energy at the top. And then lastly, just to solve the problem, at this point I'm either going to solve for H or for delta R. It doesn't matter which. What I'll do is I'll solve for delta R. I'll do that by replacing the H here in this expression with delta R sine theta, just to finish off the example. So I'll do that over here. So in my red expression there, I'm going to take the H and replace it with delta R sine theta, like so. And here's the friction term. And then kinetic energy on the right. And now at this point, I just have to solve for the displacement delta R to finish the problem. So algebraically then, I have to do the following. First of all, cancel the mass m here from each term like so. Next, I'll factor out a delta R here from each term. That'll give me this. Like so. And then lastly, just divide by the parentheses on both sides. So when I divide by the parentheses on both sides, if you look at the expression that I'm beginning to write down here carefully, it's actually the third kinematics equation, because this quantity that's here in parentheses, that's actually the acceleration of the eraser as it slows down while moving up the slope. The reason why you see the third kinematics equation pop up here all over the place in the work energy theorem is because it's really an expression of energy transfer. That's why we see it here mathematically. All right, just finishing off the problem. Let's see what we get. I'm going to do the parentheses here first. 9.8 times the sine of 30 plus 0.2 times 9.8 times cosine of 30. So multiply by 2, move it up into the numerator, and then multiply by 5 squared. After all of that, finally comes out to be 1.8. Okay, any questions on this example and the one previous before we begin to move on? Yes?
If we were to not use the identities on the test, would you mark us off because we were...
Eventually what you'll find when we do in fact get to the exam, not just the final exam here at the end of the first semester, but into the second semester when we do part 2 of this unit, is essentially everything that I'm doing in these 2 chapters can be boiled down into just one equation. And it's just that one equation that we'll use at the very end of the process. And I haven't gotten to it. Some of it, yes. Before we get to the end of the first semester, yes. Some of it we will be able to skip over. You have to see, however, some of these horrible brute force calculations to see how they work a couple of times before we get to the shortcuts. Because if I gave you the shortcuts, everybody would be like, where did that come from? It comes from this. Okay, so you got to see this a few times. Yeah.
Also, part 1 of this unit is going to be on the final.
Yes, exactly.
You
John?
said this is early 19th century physics? So
Yeah,
what did
the
they
underlying physics of the Industrial Revolution is understanding work and energy transfer.
What did they think about energy transfer before that? Like,
A lot of it was really just trial and error, because I mean, we had technology prior to the scientific revolution, prior to the 17th century, but we didn't really understand the underlying science of it. In other words, everything that we did was just discovered by trial and error.
yeah,
We would build something, and we would find that building it slightly differently worked a little bit better.
yeah.
And so that's why technology only progressed at a very slow rate prior to the scientific revolution, because it's all just done by trial and error with everybody making mistakes all over the place and just slowly improving on those mistakes. Once we understand the underlying science, that's of course when everything took off exponentially. Okay. Very good question. Why don't we just take a nice deep breath while we're at
Did you bring anything?
Nah, they were inviting all
This is fair to drive to work.
They were chopping.
Jenna, to further answer your question, one of the first inventions that came out of the Industrial Revolution, just after our realizations of understanding work and energy, was the steam engine.
Really?
Yeah.
I did,
So would you say that's the reason the industrial revolution happened? Because the work energy?
Yeah, basically. Yeah, that's the underlying physics. Yeah, we had to know what that physics said in order to be able to transfer it, like you do with a steam engine.
To create these machines or to create power sources for.
All right. At this point here, roughly midway through chapter 7, we actually digress a little bit. We use this point here in chapter 7 as an opportunity to introduce to you a very important example of a non-constant force. Now, throughout the year thus far, we've only dealt, I hate to tell you this, with the simplest possible situations. The simplest possible situations involve situations with constant forces. The reason why those situations are, quote, simple is because F equals ma becomes an algebraic equation, and the work energy theorem becomes an algebraic equation. And yes, of course, it takes practice in learning how to set up these expressions, but once you do, mathematically the expressions are easy, because it's all just a little bit of algebra afterwards for whatever it is that you're solving for. If you have non-constant forces, however, then the only way to treat a non-constant force by using either F equals ma or the work energy theorem is with the methods of calculus. One of those non-constant forces is introduced here in chapter 7 because even with the methods of calculus, it's actually relatively easy to describe. And it is, as I said, a very important example of a non-constant force. Yeah. The force is somewhat innocuous at first. It's the force acting on a mass due to a spring. What is just referred to generically as the spring force. Now, when a force acts on a mass due to a spring, it causes a very important type of motion. This motion occurs throughout the natural world. It also occurs all over the place in engineering and technology. I'll demonstrate that motion to you in the following way. Take a spring, hang it from this attachment, attach the mass to the spring, and then just let it go. This very important type of motion is referred to as an oscillation. Motion. The spring force causes is called oscillation. Oscillations occur throughout the natural world. Whenever you have a stable system of some sort and disturb it, the resulting motion is an oscillation. That's the case here, for example, with a mass attached to a spring. It's also the case, for example, if you have a pendulum that is hanging from a string and you just move it to the side, it undergoes an oscillation. Oscillations are also the starting point, for example, in describing anything associated with the transfer of energy by waves. whether they be, say, ocean waves propagating along the surface of the ocean itself, or sound waves propagating through this room as I speak to you, or seismic waves through rock, or even in the case of light waves propagating through a vacuum. The basic description of the energy transfer associated with waves always begins with an oscillation. Oscillations also occur throughout the engineering world as well. For example, an oscillation is always the basis that we use for keeping track of time. All clocks, regardless of how simple they may be or how complicated they may be, have at their heart a timing element. An oscillator is a perfect example of a timing element. It would actually be a rather poor clock, but what I could actually do is use this bobbing weight on the spring as a means of keeping track of time. All mechanical clocks, electronic clocks, and even atomic clocks have at their heart an oscillator. Oscillators also pop up in other places as well. For example, alternating current. The alternating current coming out of an ordinary wall socket anywhere in the United States is an oscillator where the current itself is oscillating back and forth with a frequency of 60 hertz, 60 oscillations per second. This is the standard that is used in power generation in the United States. This is why the frequency of our spark timers, for example, in our spark timer experiments, that's why the frequency is 60 hertz, because it's the same as the frequency of the alternating current coming out of the wall sockets themselves. So oscillators occur as a type of motion throughout the natural world. It also occurs all over the place in engineering applications. And it all starts with beginning to understand how the spring force works. Henry?
No, never mind.
Okay. Yes, Griffin?
Is that why, like, if you said if you charge your phone or something while we use those smart timers,
It interferes with their operation, that's right. Okay, now, it turns out that the spring force is actually very easy to describe mathematically. But before we get to those details, I have to mention a couple of things about the spring itself. The spring is idealized. That means that we ignore some complications associated with the spring for simplicity. The first thing that we ignore is the mass of the spring itself. We consider the mass of the spring to be negligible compared to the mass of the object that it's attached to. So therefore, we think of the spring as massless. So if it doesn't have any mass, that means it has no weight, nor does it have any inertia. Now, of course, that's not really the case. If I take the spring, for example, and hold it horizontally, it sags a little bit under its own weight. We ignore it. If I take the spring and hold it vertically, it sags a little bit under its own weight. We ignore that completely. And secondly, we also assume that there is no physical difference between stretching and compressing the spring. Now, here's what I mean by that. In reality, of course, there is a difference. If I take the spring and just hold it so it's not stretched or compressed, this is referred to as the spring's equilibrium position. And then, yes, I can stretch out the spring like so, quite a large distance from the equilibrium position. But I can't do that so much in compressing the spring. I can only compress it a little bit. I'm actually physically constrained by the structure of the spring itself from compressing it a large distance. We ignore that completely. We assume that stretching and compressing is the same thing. And then lastly, third, if you take a spring or any elastic object for that matter, such as a rubber band, for example, and then very rapidly stretch and compress it like so, if you've ever done this with a rubber band yourselves, what do you notice about the temperature of the rubber band after you do this? It's warmer. The reason for that is because in a pretty complicated way at the molecular level, basically the energy of you stretching and compressing the spring is being converted into heat within the mechanical structure of the spring itself. In the case of a metal spring, by the way, when I do this, I actually generate radio waves when I do that. We ignore all of that completely. We assume that there's no heat generation. So in other words, by idealizing the spring in this manner, we're simplifying the picture considerably. Okay, now with those simplifications in mind, it actually becomes very easy to describe the spring force itself. Here's how I'm going to go about doing this. I'll do this as a demonstration as well. What I'm going to do first is take the spring and just hang it vertically like so, such that it's in this unstretched and uncompressed position. We usually note this as a dotted line like so, and this is referred to as the equilibrium position. So if I just take the spring, for example, like so, hang it vertically from this attachment, yes, in reality, it sags a little bit under its own weight, but once again, we ignore that. This right here is the equilibrium position. Now I'm going to take this object here. We'll call this object here mass M. I'm going to attach it to the spring, but I'm not going to set it into oscillation. Instead, in this case, what I'm going to do is just lower it like so, have it sit here at rest, and I displace the spring some distance from its equilibrium position. This displacement here is just generically referred to as x. So now what I do, I'm going to take a mass M, attach it to the spring like so. So it's just sitting here at rest now. It's not oscillating or anything like that. Its acceleration is equal to 0. And then with respect to the equilibrium position, I displaced it here a distance. That distance from equilibrium is just generically referred to as x. Okay, now right now, the two forces acting on this mass, the weight downwards and the spring force upwards, are just canceling each other out. So right here is mg downwards for the object, and then canceling it out upwards is the spring force. I'll just call that F spring. So because it's just sitting there, F spring is equal to mg. Okay, now what I'm going to do is detach this mass m like so, and I'm going to replace it with this one. This one here is twice as much as this one. So if this one is m, this one here is 2m. So I now take 2m, attach that to the spring like so, displace it from equilibrium, and notice immediately that it displaces the spring a greater distance from equilibrium than it did a few moments ago with just the mass m. So now in that situation, it looks like this. So right here is 2m. Once again, it's just sitting there. It's not oscillating. It's just sitting there at rest. The acceleration is equal to 0. Once again, for reference, here's the equilibrium position. Yes, I obviously displaced the spring a greater distance from equilibrium. Let's call this displacement here x prime. Once again, however, the object is just sitting here. So because it's just sitting here, the forces acting in this case also cancel each other out. We have the weight downwards, and we have the spring force upwards. However, in this case, the weight downwards is not mg, it's 2mg. So then therefore, the spring force here acting upwards in this case, call it F spring prime, has to be different than this value of F spring over here. This F spring prime, as I'm calling it, notice is equal to 2mg. So because this original spring force here was just equal to mg, whereas this one over here is equal to 2mg, this then means immediately that F spring prime is twice as much as the original F spring. So qualitatively, what this means is the following. The greater that I stretch out the spring from its equilibrium position, or alternatively compress it, the greater that I stretch out the spring from its equilibrium position, the greater the spring force. In this case, I doubled the spring force from one value here to a greater value here when I stretched out the spring a greater distance. This is actually obvious if you think about it. I can even feel it in my hands. When I displace the spring only a small distance from the equilibrium position, I only feel a small amount of spring force. However, as I stretch out the spring more and more from equilibrium, I can feel the spring force acting on my hand getting larger and larger. So this then means that as the object oscillates and it displaces the spring different distances from the equilibrium position, the value of the spring force is changing. In other words, the value of the spring force is not a constant. And therefore, the spring force is not constant. So then therefore the acceleration of the oscillator is not constant. Now it turns out that describing the magnitude of the spring force is actually really easy to do. What I'm about to describe to you is an empirical property associated with springs. This empirical property is very easy to see if I do the entire demonstration for you, essentially all at once. Think of it now like this. So once again, here's the equilibrium position. Here's the mass m attached to the spring, displaced from equilibrium. Here's the distance x. Then take this guy off, replace it now with a 2m like so, attach it to the spring. Here's the distance x prime. Here was the original distance x. Here's the distance x prime. What do you suppose is the relationship between the two? It's double. It's twice as much. This is an empirical property associated with the spring. That is, the value of x prime in my demonstration is twice as much as the value of x. This then means the following. It means that the magnitude of the spring force is directly proportional to the displacement from equilibrium. Because basically all that I've done here in this problem is I went on one value of displacement to another that was twice as much, and when I did that, I doubled the spring force. So then therefore, the spring force, the magnitude of it, is directly proportional to the displacement x. This is an empirical property associated with springs. In other words, if I do this demonstration as I did, by doubling the displacement x as I did, I doubled the spring force. If I tripled the displacement, I tripled the spring force, and so on and so on. There's a direct, simple, linear relationship between the spring force and the displacement from equilibrium. Now, when quantities are proportional to each other, as I just wrote down there in my last step on the right-hand board, that then means that there is some coefficient present that turns the proportionality into an equals sign. That coefficient is written out in the following way. We used the letter K, a lowercase, to describe this coefficient. This coefficient right here is called the spring constant. The spring constant is an empirical property of the spring itself. It's basically, and I'll demonstrate it for you very easily in just a moment, a measurement of how stiff or how loose the spring is. It's a measurement of its rigidity. Measurement of the rigidity of the spring. Now here's how I'll demonstrate it for you very easily after I Sorry. Yeah, I'm not going to use this spring here to demonstrate the spring constant. Instead, I'll use a couple of other springs. What I'll do first is use here a very loose spring. Because this is a very loose spring, like a little slinky, if you will, this has a very small spring constant associated with it. The value of K is a small number. And then what I'll do is just hang this guy here like so. And then I'll attach to it this rather small mass like this. And I'll attach it like so and then set it into oscillation. And when I do, the frequency will be rather low. You'll also see that the weight itself doesn't move very quickly. So the frequency here is maybe about 1 hertz. It's maybe about 1 oscillation per second or so as I set this into oscillation like that. Okay, now compare this oscillator here to this oscillator here, where in this case, this spring is a lot more rigid. So if this spring is a lot more rigid, that means that its spring constant, its value K, is a big number. And then watch what happens when I attach the same mass here to this spring and then set it into oscillation. Notice that the frequency in this case is obviously a much bigger number than it was in the previous situation. So the kinematics of this motion of an oscillation is in part determined by the stiffness of the spring. If the spring is very loose, as you saw originally, this is a small number. If it's very stiff, this is a large number. This relationship that was discovered by the spring force is named after its discoverer. This person was a contemporary of Isaac Newton. It's actually named after Robert Hooke. This is called Hooke's law. How many of you watched the reboot of the Cosmos series last year when it was being hosted by Neil deGrasse Tyson? One or two of you did. I highly encourage you, by the way, to watch that series. One of the episodes actually focused on Robert Hooke, and it happened to mention this discovery. Now, when it comes to the spring constant, as I said, it's an empirical property. That means that it's something that is measured. It's actually really easy to measure. That's in fact what we'll do at the beginning of class next time. We'll do a short little mini lab where you'll measure the spring constant of one of these springs. It takes about 10 minutes to do. Okay, let's take a look here at the agenda board to finish up for today. Don't forget about the web assignment that is due on Friday of this week. You did at this point, by the way, very easily do the web assignment problems. That's it for today.